In this video, we're going to be continuing our discussion of chemical kinetics, and the topic that we're going to be covering today is reaction mechanisms. So, what are reaction mechanisms? So, reaction mechanisms refer to the details about the individual steps that comprise the overall chemical reaction, right? So, um, within a chemical reaction is a series of steps that start with the reactants and end with the products. So um, we call these individual steps in a reaction mechanism elementary reactions, which just refer to the individual steps that comprise the overall reaction, right? So there are several features of elementary reactions that we want to consider. So as I said before, elementary reactions are individual chemical reactions that occur in a single step, right? That's a key distinguishing feature from reactions that are non-elementary, which are multi-step reactions. And the rate law expressions for elementary reactions and the type of elementary reaction that occurs depends on its molecularity. So, what is the molecularity? The molecularity of elementary reactions refer to the number of reactant species, which include atoms, ions, or whole molecules involved in a reaction step. And by involved, I could also mean like reactant species that are colliding, because as I said before, reactions occur when molecules collide, right? So um, let's go through the three main forms of molecularity in elementary reactions. So there's unimolecular elementary reactions, which refers to one reactant species involved or colliding in one step, where in this generic formula here we see that A, the reactant, is converted into products, where the rate law would be K equals the K times the rate constant times the concentration of A, which is considered first order, where the reaction order is 1, right? For bimolecular elementary reactions, this refers to two reactant species involved or colliding in one step, and there are two cases of bimolecular elementary reactions. So the first case is where the reactant species are identical, where two reactants are the same. So in this example here, there's 1 mole of A, and then there's another mole of A, which can be expressed as 2 times A, which gives you the products, where the rate is equal to the rate constant times the concentration of A times the concentration of A again, which is equal to the rate constant times the concentration with a reaction order of 2. And then for the second case, the reactant species that are participating in this elementary reaction may be different, where a reactant A reacts with reactant B, where the rate law is equal to K times the concentration of A times the concentration of B. And then for termolecular elementary reactions, exactly 3 reactant species are involved or collide in a single step, and there are at least 2 cases for termolecular elementary reactions. There could be more, but I'll just go through these 2 key cases. So in case 1, 2 of the reactant species are identical, not at least 2. So 2 of the reactant species are identical, where A plus B yields products, or 2A plus B yields products, and then the rate law is equal to K times the concentration of A times the concentration of A times the concentration of B, right? Which is also equal to the rate constant times the concentration of A with a second reaction order times the concentration of B, right? Overall, the reaction order would technically be the overall reaction order for this rate law would be 3, but just yeah. And then for the second case, the reactant species are different, where A plus B plus C yields us products, where the rate law is equal to rate, which is rate equals the rate constant times the concentration of A times the concentration of B and times the concentration of C, with a third reaction order overall, right? Now, you may be asking, um, stoichiometric coefficients don't necessarily suggest the don't necessarily suggest the reaction order of individual reactants, and that is true. However, in the case of elementary reactions, so an important note that we want to make about the rate law expressions for elementary reactions. So the reaction orders for reactant species can be determined directly from stoichiometric coefficients of reaction only if the reaction is elementary. That's a key that's a key factor here. If the reaction is an elementary step, we can assume that we can determine the reactant orders for the reactant species directly from the stoichiometric coefficients. Okay. Now, another key feature of reaction mechanisms or elementary reactions is that they can also vary based on the speed of the reaction. So the rate so some steps may have faster reaction speeds, others may have slower reaction speeds. However, one particular step that we want to pay attention to is the rate determining step, which refers to the slowest step, the slowest elementary reaction in the reaction mechanism, which limits the rate at which the overall reaction proceeds. So this could also technically be called the rate limiting step, given that this step limits the rate at which a reaction proceeds, right? Also known as rate limiting step, right? Okay. So with this in mind, knowing the basic features of elementary reactions, let's consider key focuses when we want to study reaction mechanism. So the first focus is that the sum of the elementary steps or the sum of elementary reactions must give the overall balanced equation of reaction. So it must give the overall balanced equation. It must give the overall reaction equation. Okay. So in this example here, this is the overall equation, right? So 2NO plus Cl2 gives us 2NOCl, right? Now, these are the elementary steps. So this is elementary step 1 and elementary step 2, okay? So we have NO plus Cl2 gives us NOCl2. And then we have NOCl2 plus NO, which gives us 2 NOCl. Now you may be wondering, or so to add the equations together, actually, let's go through that first. To add the equations together, we consider what's left, and what we want to do is cancel out any possible intermediates in the reaction. So here we can identify 2 intermediates here, because the intermediate here, which is NOCl2, is not present in the overall reaction. So we can simply cross these out, right? Because we cross out we want to cross out any products with reactant. So there's one reactant on the product side, there's one intermediate on the product side and one reactant on the there's one intermediate on the reactant side. So it's helpful to think of this as reactants and products, right? So we want to cancel out reactants with products. So we see that NOCl2 is present on both sides, so we can cross those two out. And then we just essentially add the sum of the reactants together. So we can see here that there is 2 NO molecules, or 2 moles of NO, one from step 1 and one from step 2. So this is 2 NO molecules in the first step. I mean, this is 2 NO molecules in the overall reaction. We can see that there's one Cl2 group, which is present in the overall reaction, right? And then there's 2 NOCl, which is the only product on the product side. So we can just simply put this down as 2 NOCl, which gives us the overall reaction. But yeah, that's essentially it. So essentially, you're thinking of the reactants on one side, products on the other side, and then you add the sum together to give the overall reaction. Okay? So let's go into the concept of intermediates a little further. So intermediates are species produced in one step and consumed in the subsequent step. So we can see here that NOCl2 was produced in the first step, but it was later consumed in the second step. So they should not be present in the overall chemical equation, okay? The second focus that we want to identify when studying reaction mechanisms is the rate determining step. So the rate determining step, which is the slowest step of the overall reaction mechanism, provides us with the rate law for the overall reaction. That's a very key feature here of reaction mechanisms. The rate determining step will provide us the rate law, okay? So let's go through the same example. So we're going to use the same example. 2NO plus Cl2 yields 2NOCl, right? So we want to identify the rate laws here. So for step 1, the rate law here is K1, the rate constant, which is K1, times the NO times the concentration of NO times the concentration of Cl2. However, it's super important here that we also identify the fact that step 1 exhibits an equilibrium reaction. So step 1 is considered a reversible reaction and therefore experiences equilibrium, where the forward reaction rate is equal to the reverse reaction rate. This is especially important for reaction mechanisms. We want to identify this, and therefore the forward reaction K1 is equal to K1 times the concentration of A, which is equivalent to the reverse reaction, which is equal to K1 K inverse 1 times the concentration of the products. So let me just identify this clearly for you guys here. Forward, reverse. Okay, so we want to clearly identify that. And this will be important later down the line, but we'll come back to that in a second. And then for the second step, the rate for step 2 is the rate determining step. So why is step 2 the rate determining step? Because this step is the slowest step in the reaction, given that there's only 2 steps, but still, this is the slowest step. So the rate determining step will determine the overall rate law for the overall chemical reaction. So the rate law for the rate determining step is equal to K2 times the concentration of NOCl2 times the concentration of NO. Okay? So these are the 2 rate laws that we've found. However, there's a problem here. The rate law for this equation is incomplete because we can't express intermediates, which in this case is NOCl2, right? We can't express intermediates in the overall rate law. So we need to find a way to express intermediates using only the concentrations of reactant species and relevant rate constants. Okay? So this is why we have this information here. So we can use the information from reversible reactions that experience equilibrium to express the concentration of intermediates in terms of the concentration of reactant species and relevant rate constants. Okay, so that's why we want to pay attention to equilibrium reactions. So from step one, we remember that the forward reaction is equivalent to the reverse reaction, where the forward reaction is equal to K1 times the concentration of NO times the concentration of Cl2, which is equivalent to K negative or K inverse 1 times the concentration of NoCl2. So we can express the concentration of NoCl2 in terms of reactant species, in the concentration of reactant species, and the relevant rate constants. So from this, we isolate or solve for the concentration of NoCl2 by moving everything to one side, as I've shown here in this equation below, right? And then we can substitute this. We can substitute for this concentration. We can substitute for the concentration of the intermediate NoCl2 using this expression into the rate law to determine the overall rate law, where the rate law is equal to K2 times the concentration of NoCl2 times the concentration of NO. We substitute the expression that we determined earlier, which is K2 times the concentration of K1 over K inverse 1 times the concentration of NoCl times the concentration of NO times the concentration of Cl2 times the concentration of NO twice. So what we're left with is essentially the rate of the overall the rate law for the overall reaction is equal to K2 times the concentration of K1 times the over the inverse rate constant, or K inverse 1, times the concentration of NO2 to the power of 2 over times the concentration of Cl2. I believe that this would technically be a third order reaction given the molecularity of the rate law. So this is the overall rate law for this reaction. Okay? Now, let's summarize how to solve reaction mechanism problems. So there are two key things we need. We need the overall balanced chemical equation. So to do this, we want to list out the elementary reactions in order. We want to cancel out intermediates and catalysts, which we'll get into in the next topic. And the sum of the elementary reactions must equal the overall chemical reaction, and there should be no catalysts or intermediates present. Now, the overall chemical rate law, okay, that's the second thing we need to find. So to do this, we write out the rate laws for all elementary reactions and identify the rate determining step, where the rate law for the overall reaction is equal to the rate law for the rate determining step. If the concentration of the intermediate is expressed in the overall rate law, we want to find the substitute expression that expresses the concentration of the intermediate in terms of the concentration of reactant and relevant rate constants. So we want to look for equilibrium or reversible reactions where the intermediate is involved, so you can determine the substitute expression by solving for the concentration of the intermediate.